We present PlenVDB, a memory-efficient VDB-based Radiance fields for fast training and rendering. The input of our method is a set of sparsely sampled images from different views. And after training, the scene is reconstructed in our model. Then fed with arbitrary novel views, the model can render the corresponding images, even on a mobile device within real time. For this novel view synthesis task, recent works have explored different data structures for representing scene information, but few have been able to balance efficiency in terms of access speed and storage footprint. Therefore, we first use VDB as the sparse volume data structure for NeRF acceleration, and achieve fast rendering. Besides, we propose a strategy that learns the VDB directly and achieves fast training and occupies small storage. Moreover, the trained VDB model can be used in the traditional graphics pipeline. Now let us dive into the details, starting with the background. NeRF utilizes a MLP to model the scene. Although the MLP resolves the issues of resolution and storage, the query to MLPs is time-consuming, compared with the fast memory access. The training time often reaches hours or even days, thus limiting its applications. To speed up, DVGO directly optimizes a dense grid to represent the scene. Since the dense grid supports super-fast voxel access, it is convenient to perform trilinear interpolation and accelerate training. However, due to the sparsity of the scene, the dense grid is inefficient for storage. So, is there a data structure that balances between storage and performance? We are glad to introduce our PlenVDB. For users, the VDB is an infinite dense grid. Input a 3D coordinate, it will output the corresponding value or together with 8 neighbor values within constant time on average. For developers, the VDB is a 4-layer B+ tree. When querying the voxel 1, the accessor will cache all visited nodes. As the tree depth is 4, the access is fast. And when the next query, 2, is the neighbor voxel, the VDB will check the accessor bottom up, which often hits for the first check. Thus, the VDB is able to perform fast trilinear interpolation and ray marching. Generally, the VDB enjoys the best of the both sparse and dense volumes. Therefore, we believe that VDB has great potential as a data structure for NeRF. We choose DVGO as our baseline and replace its dense grid to VDB. To demonstrate the effectiveness of the VDB data structure, we follow the training strategy of DVGO. We use 2 VDBs to represent the density field and color field, and gradually represent higher resolution scene information as training progresses. In order to learn directly on VDB, we designed 3 VDBs to support PyTorch training pipeline. Given a coordinate, we perform trilinear interpolation to query the value in the data VDB. Then calculated by volume rendering and loss function, the gradient will be back-propagated. We accumulate the gradient into the grad VDB. When the optimizer calls the step function, we utilize the intermediate op VDB to update the data VDB. Finally, we only use data VDB for fast rendering. Since VDB is fast to access neighbor values, we are able to perform fast trilinear interpolation and accelerate training stage. For an image, we allocate 1 CUDA block and perform ray marching twice for each ray. The first ray marching visits only the density to count the number of the points that make valid contributions to the pixel. In the second time, we read out the color features and use MLP mapping to generate the color. Since VDB is fast to access neighbor values, we are able to perform fast ray marching and accelerate rendering stage. For better performance and storage, we merge the 2 VDBs to one that saves the indexes pointing to the active voxels stored in an additional buffer. In this way, we can reduce the topology redundancy. Finally, without any special optimizations, our PlenVDB achieves NeRF comparable QLT within minutes. And the speed is close to the state-of-art works for training acceleration. Based on DVGO, our PlenVDB achieves 4 to 5x speed-up with well-established rendering technology, and reduces the memory occupancy for about 8 times. Here we present our quantitative results. It is worth mentioning that the reason why our method and DVGO are far inferior to Plenoctrees and Plenoxels in terms of rendering speed is due to the difference in the way the colors are modeled. rather than the inferiority of the data structure. The spherical harmonic coefficient modeling approach they use is able to dispense with the matrix operations of MLP and requires only a simple weighted sum. We also showed in rebuttal that using VDB to represent the spherical harmonic coefficients can also achieve comparable rendering speeds. To demonstrate the potential of VDB, we also compare it to the sparse octree in a nearly dense grid. Under the condition of representing the same scene information, VDB achieves a better balance in terms of accessing data and storage space efficiency. We also perform ablation study on the optimization during rendering stage to further demonstrate the efficiency of our method. Here we present some videos for rendering quality comparison.